I hope you are able to see the problem. So as we discussed last class, we were discussing about heat exchanger, right? So in heat exchanger, the first question we will discuss an oil cooler of the form of tubular heat exchanger cools oil from a temperature of 90 degrees Celsius to 35 degrees Celsius by a large pool of stagnant water. Assume the constant temperature of 28 degrees Celsius. The tube length is 32 meter and the diameter is 28 millimeter. And the specific heat and specific gravity of the oil are 2.45 kilojoule per kilogram Kelvin and 0.8 respectively. The velocity of the oil is 62 centimeter per second. Calculate the overall heat transfer coefficient. Okay. So here, if you see the question, first we will write what are the parameters which is given. Okay. So in that, first one is hot fluid, that is oil here, and cold fluid is water. Okay. Now the temperature is T1 and T2 we are taking. Cold fluid we are taking small letter T1 and T2. Now entering temperature will be the temperature of oil, that will be T1, that is given 90 degrees Celsius. Okay. And exit temperature of oil will be, that is T2, it is given 35 degrees Celsius. Okay. And the entry and exit temperature of water is given, that is T1 is equal to T2 is equal to 28 degrees Celsius. Now the tube length, that also given, it is L is equal to 32 meter and diameter it's also given 28 millimeter, which means 0.028 meter. Okay, now specific heat capacity CPH also given 2.45 kilojoule per kilogram per Kelvin. So that you can convert it into 2.45 times 10 to the power 3 joule kilogram Kelvin. Okay, now specific gravity is given, that is 0.8, and velocity c is given, it is 62 centimeter per second, that is 0.62 meter per second. So these many details are given in the question. Now what we have to do in the sense, we have to just calculate whatever they asked, calculate the overall heat transfer coefficient. Okay. Now for doing that, first we will, it is already given that specific heat gravity. So specific heat gravity will be density of oil divided by density of water. So it will be 0.8, then density of oil we don't know, 1000 of density of water, then density of oil rho 0 will be 800 kilogram per meter cube. So we will get this one. Now we have to calculate mass flow. So mass flow rate of oil will be mh, that will be rho 0 times A times C, that we can write as 800 times pi by 4 times d square times 0.62. Okay, then you have to calculate, you will get the answer will be 0.305 kilogram per second. Okay, now we have to calculate the heat transfer Q. Q will be MC CPC times T2 minus T1. It will be, just you have to submit, you will get the answer 41 times 10 to the power 3 watt. Okay, so first you please go through this, then we will see the remaining portion and we will find the value of temperature. Hello Likit, are you following? Okay, after this what we have to do? So here what we did, we found the Q value, then after that Q means heat transfer, we found it. Now we have to, we know that one more formula, Q will be U A delta Tm. Okay, so now delta Tm is what? It is logarithmic mean temperature difference, that is LMTD. Okay, that we discussed already in the last class. And for parallel flow, what will happen? LMTD delta Tm will be T1 minus small t1 minus T2 minus small t2 divided by log T1 minus small t1 divided by T2 minus small t2. Okay, now you just substitute the value. So here value is the 90 minus 28 minus 35 minus 28 divided by log of 90 minus 28 divided by 35 minus 28. So the answer will be, you will get 25.2 degrees Celsius. Now what you have to find? So this it is given. Now you have to calculate the Q value. So it will be UA delta TM. That's we already now all the details are available. So you have to calculate. Here you have to calculate U value. So what will give and Q is already we found that from the earlier session. If you see 41. So just substitute that 41 times 10 to the power 3, that is equal to U times area will be pi dl. So pi times dl value 0.028 times 32 times 25.2. From here you will get the value of U will be 577.9 web per watt per meter square Kelvin. So this will be the final answer. Just go through it once. So here what we did is first we wrote every parameter, whatever the parameters given here, so that we first concluded. Then first you have to calculate the heat transfer. For calculating heat transfer, we should know the mass from the gravity. Like we found the specific gravity of the oil, we found the mass flow. From that mass we got it, and using that mass we calculate the heat transfer. From the heat transfer, first we calculated the logarithmic temperature, mean temperature difference, LMTD, and then LMTD to this overall heat transfer coefficient that we found. Now we'll go to the next problem. Next problem is a parallel flow heat exchanger is used to cool 4.2 kilogram per minute of hot liquid of specific heat 3.5 kilojoule per kilogram Kelvin at 130 degrees Celsius. A cooling water of specific heat is given 4.18 is used to cooling purpose at the temperature of 15 degrees Celsius. The mass flow rate of cooling water is 17 kilogram per minute. Calculate the following. So here you have to calculate the outlet temperature of liquid, outlet temperature of water, and effectiveness of heat exchange. Take care. So these three parameters you have to calculate. So for calculating that, first we will tabulate what are the things are given. Okay. So overall heat transfer coefficient is given, that is 1100. Okay. Now heat exchanger area is given, that is 0.30 meters square. So these two parameters given, and the remaining parameters which is given, mass flow rate mh is given, that is 4.2 kilogram per minute, so that it will be for like 0.07 kilogram per second. So this will be very important. And specific heat is given cph, that will be 3.5 kilojoule kilogram per kelvin, and specific heat. So now cp h, this one you can write it as 3.5 times 10 to the power 3 Kelvin. Okay, now the inlet temperature T1 is given, that is 130 degrees Celsius, and heat transfer Cph is given 4.18 times 10 to the power 3 kilogram per Kelvin, and small letter T1 inlet temperature of cooling water, that is it's given 15 degrees Celsius, and mass flow rate mc which is given 17 kilogram per minute. Okay, so that you can write it as 0.28 kilogram per second. So these many parameters given already. Now what we have to do is, so first one, you have to find the outlet temperature of the liquid T2, capital T2, and outlet temperature of water, that is capital means small letter T2, and effectiveness of heat exchanger, that you can representing epsilon. So now capacity rate of hot water. So capacity next time Cph, it is 0.07 times 3.5 times 10 to the power 3. Okay, so that value will be 245 watt Kelvin. Okay, now it is capacity rate of liquid will be, this is hot liquid, this is capacity rate of liquid, so it will be mh time Cph, that will be 0.28 times 4.18 times 10 to the power 3. So it will be 1170.4. Now from the first, these two, this we can call it as equation 1, and this we can call it as equation 2. From equation 1 and 2, C minimum will be 245 and C maximum will be 1170.4 Kelvin. Now what will happen? C minimum divided by C maximum ratio. Okay, it will be 0. If you calculate this ratio, it will be 0.209. And now number of transfer unit you have to calculate. NT, number of transfer unit, it will be UA divided by C minimum. From that you will get 1100 times 0.30 divided by 245. The value will be 1.34. Okay. After that, now we calculated so we calculated NTU value. Now maximum possible heat transfer, Q maximum will be C minimum times T1 minus small t1. It will be, you will get the answer. Substitute the value. C minimum we already found, and capital the T1 and small t1 is already available. So you will get the value 28.175 watt. So actual heat transfer will be what? Q is equal to epsilon times Q max. So it will be 0.64 times 28.175. That answer will be 18032 watt. Okay, now that heat transfer Q will be MC CPC T2 minus T1. If you substitute all Q values given, everything is given, only T2 you have to find from that. That you will get 18032 in 18,032 is equal to 1170.4 T2 minus 17557. 556. From that you will get the value of T2 will be 30.40 degrees Celsius. So outlet temperature will be 30.40 degrees Celsius. Now we know that Q is equal to MC CPC times T1 minus T2. So it will be 18. Again we have to calculate 32 is equal to 0.07 times 3.5 times 10 to the power 3, 130 minus T2. So from that we have to calculate the value of capital T2. Outlet temperature of liquid T2 will be 56.4 degrees Celsius. So these are the question asked. So if you see here, it's a like big problem. So it will be a parallel flow of heat exchanger is used to cool 4.2 kilogram per minute. So heat specific heat is given and temperature is given, and hot cool and cold for cold water specific heat is given and the temperature is given. Now what you have to calculate outlet temperature and outlet temperature of liquid and as well as water. So to reach that we have to solve these many. So here first we is showing that like how much is the area is given, area and coefficient also given, and you have to get the mass is given, cph value, T1 temperature of that hot liquid, that is T1, it is given, and cph value given, small letter T1, that is hot temperature of cold liquid, that is water, it is given. Now what you have to find, first you have to calculate the hot heat capacity, then from the hot heat capacity you have to calculate C minimum and maximum, then from there you have to calculate the number of transfer unit NTU. From the NTU value, so that's we found it, and Q max value, from the Q max value we calculate the total heat transfer. From the heat transfer value we are taking the T2, finding the T2 temperature. Similarly again from the Q value we are finding the capital T2 temperature of the cold liquid. Okay, so please go through it once, then we will go to the next problem. Okay, now we will go to the next problem. In a cross heat exchanger, both fluid and mixed hot fluid with a specific heat 2300 enter at 380 degrees Celsius and leaves at 300 degrees Celsius. Cold fluid enter at 25 degrees Celsius and leave at 210 degrees Celsius. So if you see here that hot fluid 380 degrees Celsius it's entering and leaving at 300 degrees Celsius, so temperature change. And similarly here 25 degrees Celsius is leaving at 210 degrees Celsius, that is cold fluid. Okay, now what you have to you have to find the required surface of heat transfer and take overall heat transfer coefficient is 750 is given, mass flow rate of hot fluid is given. Now you have to, we will write what are the things are given here. So entry temperature of hot fluid, that is T1, it is given 380 degrees Celsius. So this is T1 and T2 is 300 and this is small t1 and this is small t2. Now what are other things it's given? It's given the U value, heat transfer coefficient. U value is given 750 and similarly mass flow rate of hot fluid, that is mH also given 1 kilogram per second. Now you have to calculate heat exchanger area. To calculate that, first we will calculate LMTD logarithmic mean temperature value. So for that it will be delta Tm is equal to capital. It is for counter flow, so it will be T1 minus small letter T2 minus T2 minus small letter t1 divided by log of t1 minus small t2 divided by t2 minus small t1. Okay, substitute the value from the problem. It's already mentioned here. From that you will get the answer 218.3 degrees Celsius. So okay, so heat LMTD we got it. From those LMTD value, what we have to do? We have to find the heat transfer Q. Q, how you can find it? It will be MH, CPH and T1 minus T2. So it will be 1 times 1200 times 380 minus 300. So it will be 184 times 10 to the power. So this will be the answer. Now to find 2, we have to calculate the, so if we plot it in an axis, okay, so the values will be, x-axis values will be P, that will be T2 minus T1 divided by capital T1 minus small t1. So it value will be 0.52. Similarly, y value means curve value, that R will be T1 minus T2 divided by T2 minus T1. So it will be 0.432. So from x-axis value 0.52 and corresponding y-axis value will be 0.07. 0.97. So from that we will get the f value will be 0.07 and substitute this f value and all in the formula. So from the formula we got the q value. The formula is q is equal to f u a times delta Tm LMTD. So from that you will get the area. So we have all other parameters like 184.10 to the power times 10 to the power 3, that is equal to 0.97 times 750 times 8 times 218.3. From that you will get the value of A will be A is equal to 1.15 meter square. So this will be the answer for this question. So once you please go through it, then we will go to the next session. So now after this we'll go for a theory question. So it's like to explain more about heat exchanger and all. Next question, assumption made for calculating of logarithmic mean temperature difference are. So we already know that we discussed already what is logarithmic mean temperature and all, and we have started to doing problem also. And we know the formulas like for counterflow and for parallel flow, everything we know now. So just knowing that, just you have to answer this assumption made for calculation of logarithmic mean temperature difference. So first one is constant overall heat transfer coefficient, and kinetic energy and potential energy changes are negligible. And third option is like there is no conduction of heat along with the tube of heat exchanger. So these three. So which one is correct statement? So first option all are correct, and second 1 and 3, third option 1 and 2, and D option 2 and 3. So what will be the answer for this? So the reason with these three assumptions made like during heat exchanger between two fluids, the temperature of fluids change in the direction of flow. Okay, there occurs a change in the thermal head causing the flow of heat. So there will be constant heat transfer will be there, and the only temperature changes only will happen. The fluid change in the direction of flow, and consequently there occur a change in the thermal head causing the flow of heat. Okay. Now let us go to the next problem. So similar kind of problem you already seen in the your assignment. So the parameters given for parallel flow configuration, you have to calculate the minimum flow rate, and similarly you have to calculate the heat transfer coefficient for required condition, and similarly you have to, for if you are considering it as a counterflow configuration, you have to determine the minimum flow rate, everything. So here in the deionized water and processed water, so two conditions are given. So first we will read the question. Deionized water flow through the inner tube of 3 millimeter diameter in a thin walled concentric tube heat exchanger of 0.91 meter length. The hot process of water at 95 degrees Celsius flow at the annual form of the outer tube of 60 millimeter diameter. The deionized water is to be heated from 40 degrees Celsius to 60 degrees Celsius at the flow rate of 5 kilogram per second. The thermophysics properties of the fluids are. So the properties is given. I'm not going to read it. You can see it from the screen. And you have to calculate three things. That is, first one is considering a parallel flow configuration of heat exchanger. Determine the minimum flow rate required for the hot process water. So that is the first question. And the second question, determine the overall heat transfer coefficient required for the condition of part A. So part A is the parallel flow configuration. Okay. And third is considering a counterflow configuration, determine the minimum flow rate required for the hot process water. What is the effectiveness of the exchanger for this situation? So these three things you have to calculate. So for calculating that, first we will go through the diagram. Okay. So see in this diagram, so we given that it's from the question, we marked everything accordingly. So processed water we are considering H, and deionized water is C. Okay, so THI, the temperature will be 95 degrees Celsius, and T2 is the, then delta T1, the mean difference temperature you have marked here, and the remaining what? And if you see here, delta means TCI 40 degrees Celsius is given, and TC 60 degrees Celsius is given. So the other parameters also marked here. So from this only we have to calculate the three problem. Okay. So we were taking actually three assumptions here. First one, negligible heat loss to the surrounding. So surrounding heat loss we are considering as neglecting, and kinetic energy and potential energy changes are we are neglecting. So first, from the overall heat energy balance, you have to calculate like Q is equal to mc of h. Okay, and thi minus tho is equal to mch tco minus tci. Okay, for a fixed term like thi and comma mh will be a minimum when it will be minimum. When you know when it will be minimum means th0 is a minimum. If th0 is minimum, then thi and mh will be minimum. Now mh minimum we have to calculate. For that mc of c tc0 minus tci divided by ch thi minus tho, that will be, you have to substitute. So here everything is given, mc is given, thi is given, tci is given. So just you have to substitute these four values in the next question. So you have to calculate it through calculator, then you will get 2.85 kilogram per second. Okay, so that is our first question, minimum flow rate. So to find the minimum flow rate, this is the formula, mc of c times tc0 minus tci divided by ch times thi minus th0. So all the parameter is already given from the question. We draw this diagram. So from the diagram it is very clear for the each case of processed water and deionized water. Now this is for the A question. Now if we go to the B part of it, so B part will be Q is equal to UA delta T LM comma PF. So it will be delta T LM comma PF. That how you are calculating delta T1 minus delta T2 divided by log of delta T1 divided by delta 2. It's nothing like LMTD. So here it's determine the overall coefficient required to the condition that we are considering parallel flow. So that's why this formula came. Now what you have to do, and here delta T2 is 0 and delta TLM is 0. So U times A will be infinity. So now A is, we know that pi dl is finite. So U will be extremely large. So U value will be very large. Okay, so the heat cannot be accumulated with this arrangement. That is, the heating cannot be accumulated with this arrangement. That is the conclusion for that. So what is the determine the overall heat transfer coefficient required for the condition of part A is given. So part A, in the part A only we calculate using part A the formula of heat transfer with Q is equal to UA delta T, and first we have to check with the delta T. From the delta T value we will be this one. So delta T2 will be 0 and delta LM will be 0. Then in the formula what will happen? So delta T2 will be, delta TM will be 0 and the delta LM, if it is 0 means the whole formula will be 0. So definitely then U times A will be infinity. So if it is infinity means A, we know that it will be pi dl. So definitely A will be a finite value, then U will be very large value. So if it is U is very large value, hence heating cannot be accomplished with this arrangement. So that is the thing. Now if we go to the third part of this question, with CF arrangement that MH is will be minimum when TH0 is a minimum value. So like MH will be minimum when TH0 minimum. This requires that TH0 minimum. So this requires TH0 is minimum. So here TH0 is equal to TCI is equal to 40 degrees Celsius. From what that you have to calculate the mass. So mass will be 5 times 418 times 60 minus 40 divided by 4197 times 95 minus 40. So it will be 1.81 kilogram. Okay, now the condition is C minimum is equal to CH, which means if it is right here, C minimum is equal to CH, which means like what? So, which is cooled from THI to TCI, right? So, epsilon rate will be 1. So, if you see here, so in the question, so there will be two conditions like deionized water case and processed water case. For these two, we are calculating the minimum flow rate and determine the overall heat transfer and considering counter flow configuration. Okay, so for that from the table, first we calculated Q value formula. This only we have to take care of it in first part. THI MH is minimum, so when TH0 will be minimum. So from MH minimum value we calculated minimum mass rate rate. So it will be MCZ times T0 minus TCI, that will be CH is times divided by TCH times THI minus TH0. So it will be 2.85. Now if you find b value, b question q rate, so we have to calculate the heat like overall heat transfer of the coefficient. So if you see that you like from the formula you a delta T LM. So, okay, so delta T2 value is 0 means the delta Tm will be 0. If it delta Tm is 0 means UA value will be very high. From that A we know that it's a finite value, then U value will be very infinite, very large amount, and so from that you cannot calculate this parameter. Now if you go to the C question is considering counterflow configuration, determine the minimum flow rate. So same again as first kind of question. So minimum flow rate M will be, you have to calculate from 5 times 418 times 60 minus 40 divided by 4197 times 95 minus 40. It will be mass value you will get it. And C minimum and CH is equal means the epsilon value also will be 1 for this case. So there is one more question, but it's running out of time. What we will do, like please note this question, consider very long concentric tube heat exchanger having hot, and this just see the question. You have to calculate the hot water outlet temperature, that is capital T2. We have to calculate in both situation, counter flow and parallel flow. Try to solve this problem and then we will discuss it in the next class, the answers. Okay, so today we will stop here. Like we will continue in last class. So please follow